Hi everybody, this is Mrs. Dinkelman, and we are looking at the notes for 6.4, which has been labeled as the definite integral, calculator integration, and then also fundamental theorem of calculus. So I'm going to keep the definite integral and calculator integration here together, and then I'll make a separate video for the fundamental theorem of calculus. So far we've looked at the integral as finding the antiderivative, and that's certainly still the case, and that's certainly still kind of a process or procedure that we will do with integrals. But we are going to look at what's called a definite integral. And so I want you to notice with the definite integral, what you see here is that there are limits, and these will be numbers generally from a to b. And we call those limits not limit like x approaches infinity, but just we're going to look from here to here. When we do that, what it really means is it's helping us find the area under the curve. So we're kind of making this transition into, instead of adding an infinite number of rectangles to find the exact area, what the mathematicians discovered is it's the same as finding the antiderivative. And we'll maybe look at that a little bit more with the fundamental theorem of calculus. So when we did indefinite integrals and just found antiderivatives, we added the plus c because it basically gives us a family of curves, like it's an x squared plus c. So it's some sort of parabola, but it could be moved up or down a little bit because we didn't know what the constant was. The definite integral is a little bit different. We're still going to find the antiderivative to help us calculate it, but instead we should get a number value, and that is going to tell us actually what the area under the curve is. So on calculator integration, which is what this first part is, we're just going to use our calculator to find this. I have the 89 on here, and then I'll also coach you through the 84 just a little bit. So I have an 84 in front of me. I'll make sure that I can coach you through first. So let me do the 89 people first. Calculate this with the 89. You can see just above the 7 is that little elongated s. So we're going to go integral, and then we're going to type our function. So in this case, it's x cubed. Oops, too many x's there. Minus 6x. Just like in derivatives, we're going to go comma x. And now, just by the way, this right now is something that the 84 cannot do. If we hit enter right now, the 89 can give us the antiderivative of that equation. Okay, so that's the indefinite integral that we were doing the last few units. If we want to know the definite integral, which we do here in this situation, we're doing -3 to 1. So I always put the lower limit and then the upper. So function, comma x, then lower and upper. And then that should give us a numeric answer. So what this is saying is if we look at this cubic and we are trying to find the area under it only from -3 to 1, that we would get 4 for our answer. Okay, on the 84, and that's what Gary kind of coaches us through a little bit more here. If we go to the math menu, which is just below alpha, we'll see on number 9 for me, it says fn int, so like for finite integral. And we're just going to type that integral just as it is. Okay, so we're going to make it look exactly the same. It's really nice that the new 84s have that kind of, it's called pretty print. Okay, if you don't have one of the new 84s, it's basically a similar process to what I did with the 89. You just have to go to that, find that fn int, and then it's going to look a lot like this line where you type in the function and then comma x and then the two limits there. Okay, I'm going to go ahead and just skip to number 3 because I want to make sure we know where to find the absolute value. So for you 89 people, when we want to absolute value this function, we have to go into the math catalog. So that's up above the 5, and then number, and then there's abs for absolute value. And that's going to be x cubed minus 6x, and then comma x, comma -5, comma 5, and then we'll hit enter. I like at least at some point in the 89 it has that pretty print for us. Okay, for the 84 people, your absolute value is also in the math section. You just have to arrow over to number or NUM, and abs is the very first one. So again, under the math you can find number and then absolute value. So what you'd have to do first is go math and then fn int, and then you could type in your -5 to 5, again, for those of you that have the pretty print. And then you want to go back to math to find your absolute value. So arrow over to num or number, abs, and then you can start typing things in. Okay. Okay, it's not going to let me. Give me a second. Okay, so Gary's just talking about how that math print is a lot easier. Just like I was saying, just let me know if you have any issues with your calculators and you need to just have a little coaching on that. I would definitely love to help you. Okay, let's see what else we got here. What I didn't mention above was signed area. So unfortunately, when we do the integral, if there's part of the curve that goes under the axis, then that area will be counted as negative. And sometimes we want that to happen and sometimes we don't. So we have to be careful about that eventually. Anyhow, with this absolute value, what that does for us is it takes all of that negative area and it plops it up and makes it so everything turns into positive. So if we need area to be positive, we don't want it to do this thing where it cancels each other out, then we can always just throw absolute value bars around it. I'm not going to use the idea of signed area to evaluate that one without a calculator because I don't really want to have to deal with the 1/2 in there. Actually, maybe I'll just change the problem real quick. Let's pretend it just says x minus 1 and not 2x minus 1. So what we could do with that, because it is signed area, we could actually just draw the picture. So we know that if it's x minus 1, it's just that v that's moved over 1. And if we want to find this area from 0 to 3, then we can find just the area of those triangles and add them together, since we know that that's what integrals, at least definite integrals, are doing. So that first triangle is really a 1 by 1, and then we have to divide by 2. And this second triangle is a 2 by, well, let's figure out what this is. So that's a 3, 2 right there. So the height of that is 2. So it's a 2 by 2, again, divide by 2. So 1/2 plus 2, or 2.5 would be the answer to that integral that I made. Okay. So this one just wants us to set up the integral, and does it want us to find it? I don't think it wants us to find it. So it just is kind of getting us to get used to the fact that we're finding the area under this curve. So we set up an integral, should have a dx at the end. Just kind of by the way, remember the function is really the heights of every rectangle. That's what we used when we did Riemann sums. And the dx is that delta x, or the width of every rectangle. And an integral is really adding up an infinite amount of rectangles for us. It's technically a limit. Okay, we're only looking from 0 to 2. So that would be the setup for our finding the area in that particular curve. Okay. Okay, I'm going to stop now because I'm going to make another video for this fundamental theorem of calculus. But what I would recommend is that you get going on the assignment for the parts where you're just kind of finding the integral. So I would say this first part looks good. Maybe stop right there. So like 1 through 8, I believe, then you'll be fine. And then there's probably some review problems that you can do as well, but save this 9 through 16 or 9 through 22. We'll do those after learning the fundamental theorem of calculus.